Last class we did a little bit of work with reviewing some of the algebra concepts that we need for later on in this particular course, and that's what I want to spend part of today's class doing as well, is doing a little bit of review on those algebra concepts. Okay? The place we will start today is with the concept of linear functions. We will spend many times in this course where we will get to a problem and the question will be to write the equation of a tangent line. And right now that doesn't make a lot of sense, but it's along the same lines as writing the equation of a linear function, and so that's why I want to spend some time reviewing that here this morning. Start out with, let's say we have two ordered pairs. We've got the ordered pair 1, 2, and another ordered pair at 3, negative 4. And we want to write the equation of the line that goes through these 2 points. Graphically, what this looks like is I have a point located at 1, 2, and another point located at 3, negative 4. And I'm interested in writing the equation of this line right here. What are the two components that I need to be able to write this equation? What two things do I need to know about this line that would make it different from any other line? I would need to know its slope and also its y-intercept. Those are the two key components, right? Now, my guess is you've done a lot of work with writing equations in what we call slope-intercept form. Y equals mx plus b. The m is the slope, the b is the y-intercept. I'm going to try to not discourage you from using this form, but I'm going to try to encourage you to use a little different form that you may or may not be as familiar with. It's a form called point-slope form. And the basic setup for point-slope form looks like this. Y minus y1 equals m times the quantity x minus x sub 1. You don't have to use this form, but I think you will start to see the advantages of it as we progress through the course. It's a little easier to use this one than it is the mx plus b. Okay? In point-slope form, there are two things that you need to know. One of them is you need to know a point on your graph, and in fact we have two of them to choose from here. The other thing you need to know is the slope, which is something we would have to find for this form anyway. So the advantage of point-slope form is that we don't have to know a specific point, which is the y-intercept. We can use any other point on the graph, not just specifically the y-intercept. Okay? Now, what would this look like? Okay? Let's start by calculating the slope. Let's fill in that value for m first, and then we'll come back and fill in the rest of it. Okay? How do we find slope of a line? What are we looking for? Yes. Okay? To find the slope of any line, we subtract the y's, we subtract the x's, and then we divide that ratio. We're looking for how much did the y-coordinate change, how much did the x-coordinate change, and then slope is just defined as that ratio. Okay? So let's go ahead and do that. Right? If I let these be the like x2 and y2, if I let the second ordered pair be the second group of coordinates, and I let the first ordered pair be the first group of coordinates, okay, and then just fill in the appropriate numbers, here's what it would look like. Negative 4 minus 2 in the numerator, and 3 minus 1 in the denominator. Okay. A little bit of simplification here. It looks like negative 6 over 2, so it looks like my slope is negative 3. Right? And that's the value that I substitute in here. Now, all this means is that if we look along this line, every time that we go down 3 units, we need to go 1 unit to the right, and we will still be on the line. And then, in fact, if I go down 3 more units and 1 more unit to the right, then I land on that other ordered pair. Okay? So that's what the slope is referring to. Okay? Now, to finish off this equation, the only other thing we need to do is to substitute in for x sub 1 and for y sub 1, one of these ordered pairs. And it doesn't matter which one, I'll just go ahead and choose the first one. Okay? So I substitute in y minus my y-coordinate from the ordered pair, which is 2. And in the parentheses, it's just x minus 1, just by substituting in the x-coordinate. This is the equation of a line because it has an x and a y in it. It's just not completely simplified to what you would get if you use slope-intercept form. Okay? But this is great. If you want to give your answers in this form for writing the equation of your line this semester, that will be wonderful. Okay? Then I can really easily see where your point was at, and I can easily tell what your slope was. Okay? If you don't like this form and you want to use mx plus b, I have no problem with that either. Okay? Just whatever you're more comfortable with, I just give you a couple of options. Okay? But that's writing the equation of a line and finding the slope as well. Okay? The next major concept is more just definitions that I need to go through. We'll talk about profit, revenue, and cost, and the relation between these, because this is a business calculus course, and so we will see a lot of our word problems dealing with profit, revenue, and cost, and I need to make sure that everyone knows exactly what we're referring to when we talk about these terms. Okay? First of all, your costs are, of course, just the amount of money that you need to spend in order to make this operation happen. If we talk about Oktoberfest and selling T-shirts, of course, costs will be all of the costs that are encumbered by our organization just to get the T-shirts printed. Okay? There may be some fixed costs, which might be just the actual setting up the machine. There may be some variable costs in the number of T-shirts you print. The more T-shirts you print, probably the more it'll cost you. Okay? So there's different types of costs that are associated with these problems. Revenue is just how much money you bring in. So when we're sitting down at Oktoberfest and at the end of the day we see all the money that's in our cash box, that's our revenue. That's just how much money has been brought in. Okay? And we'll talk about a formula for this here in just a minute. And then profit is the one that combines these two together, because profit is when we have all of our revenue calculated and then we subtract away all of our costs. And these will be the symbolic notation that we use for each of these. An uppercase P will stand for profit, uppercase R for revenue, and an uppercase C for cost. Now, X in this problem, because we've got an X in each one of them, each of these three things depends on X, and in this case, X is just probably the number of T-shirts that we're talking about. Because the number of T-shirts that we make will affect our cost. It will also affect, the number of T-shirts we sell will affect how much revenue comes in, and then putting those together will affect the profit. Okay? So there's the equation for profit as it relates to revenue and cost. There's also a formula for revenue that we need to talk about. Okay? And if we're talking about sitting down at a booth and bringing in money at the end of the day, what are the two things that you would need to know if I wanted, if we talk about bringing in revenue? What would be the two things you'd have to know at the end of the day? The selling price of the T-shirt and how many you sold. Exactly. Okay? And what would we do with those two variables? You'd multiply them together. Sure. Okay? And so our formula, I'll go ahead and write it up here and then we'll define the variables here. We take X, which would be the number of shirts that we sold. Okay? So X is just the number of the item that we're talking about. Okay? Multiplied by lowercase p of X, which is the price of the item. And if we multiply those two together, that will tell us how much money should be in our cash box. That's our revenue function. Okay? Again, we will use this formula a lot. Okay? So this is another one. Be careful with this. It's a little unfortunate, but that's just the symbols that this book uses. Lowercase p is a price function. Uppercase p is a profit function. So be careful with the upper and lower case on that. Sometimes this is also called the demand function. And when we get to those applications this semester, I'll spend a little more time with that. Okay? All right. Another term that will come up a lot is when we talk about breaking even. And in terms of a profit, what does it mean for us to break even? So if we go out and sell these shirts and we just end up breaking even, what happened? We didn't make a profit. In other words, our profit was equal to what? Zero. Okay? Profit is equal to zero. Now, another way of saying the same thing here is the profit is equal to 0, what does that mean about our revenues and our costs? They are equal to each other, right? Okay. So if we end up spending $100 on these shirts and we only bring in $100, of course, then we broke even. Okay. So another way of thinking about this is that revenue equals cost. So when we get into these word problems and they start talking about breaking even, we might need to, this might be our initial equation. We just set the revenue equal to the cost and then we do our algebra from there. Okay? All right, and then one more word that comes up when dealing with these profit, revenue, and cost functions is we end up getting this word marginal in here. And marginal can be applied to any one of these three. We can talk about marginal profit, we can talk about marginal revenue, we can talk about marginal cost. Okay? For right now, the biggest thing that I want you to know is that marginal is equal to slope. It's not technically exactly equal to it, but for now that will work. Okay? When we get into the applications later in the semester, we'll spend more time with marginal. But for right now, just think about marginal as the slope. Okay? All right. Moving into another area here, we'll talk about composition next. I'm going to give an example for this one. Let's say that we've got a function f of x, which is defined as the square root of x, and we've got another function which says just take your number and add 4, so x plus 4. Okay. In algebra, we did these composition problems such as things, maybe f of g of 9. Okay? Now, what is this asking me to do? Well, the first thing it's asking, whenever we have an algebraic expression like this, we always want to start with the innermost function. And so the first question that it's asking me is to evaluate g at 9. Right? So we're going to come up here to function g, and we're going to substitute in 9, and what's the answer to that? 13, okay? 9 plus 4, 13, right? So what I'm going to do is I'm just going to rewrite the f, because I didn't do anything with function f yet. G of 9 can be replaced with its answer, which is 13, okay? And now what this is telling me to do is to take 13 and substitute it into the function f. So what really happens in a composition is we take an initial value, we substitute that into one of the functions, use that answer as the input into the next function. Okay? And in this case, the answer would just be the square root of 13. Okay? And this is composition. Now, this doesn't seem very important. Why would this help us in calculus to do composition? Okay? What we will find out is that a lot of functions in calculus can be broken down into separate functions. Okay? And what that does is it allows us to do a lot easier calculations when we get to derivatives and integrals. Okay? It's harder to look at the function as one single joined together function, but if we can split it apart into two separate functions, it's a lot easier to work with. So we will be doing some of that this semester, trying to split it apart. Okay? All right, let's just do another example here. What if I ask you to calculate g of f of 9? Okay, so what if I just switch the order of the functions, g and f? Does that make a difference in our final answer? Okay, and some of you shaking your head yes already. Okay, let's talk about what the answer is. First of all, what's f of 9? That's 3, right? We substitute in 9. The square root of 9 is 3. Then what I do is I take that answer, 3, and I substitute it into g, and what's the answer for this? 3 plus 4, which is 7. Definitely it is different than the square root of 13. So when we undo these functions, we have to be really careful to make sure that we go in the correct order, or we will not get the correct answer for what we're looking for in the calculus part. Okay, questions with that? All right. The next step in this is to not necessarily look at an individual point or an individual number, an input like 9. What if we just look at the function in general, f of g of x? So what if instead of looking at a specific number, what if we just look at all numbers, x? Okay? What would this look like? Okay? Well, I do the same thing. It's just it looks a little bit messier by the time I'm finished. What can I substitute in for g of x? What's g of x equal to? Well, it's equal to x plus 4. So what I can do is I can say, whatever my number is, I'm going to add 4 to that number. So that can be substituted in here for g of x. Okay? Now, what is f evaluated at x plus 4? Well, what am I supposed to do in function f? I'm supposed to take the square root of my number, correct? So what I'm going to do here is I'm going to take the square root of my number, and my number just happens to be x plus 4 this time. Okay? And so this is what f of g of x would equal, the square root of x plus 4. Okay? What if we go the other direction here? What if we do g of f of x? Okay. Well, first of all, what am I going to substitute for f of x? Yeah, somebody said it. Square root of x. Right. Okay. That just goes substitutes directly in for f of x. Okay. Now what I want to do is I want to take my number, square root of x, and substitute that into the function g. Okay. So instead of g of x, I'm now looking at g of square root of x. And so what will the right side look like? Square root of x plus 4, right. Okay. And just be really careful with this. I purposely wanted to pick this example. Notice these two answers don't look much different, but they're quite a bit different. Okay. One of them has the plus 4 underneath the radical. One of them has the plus 4 on the outside. And we saw before that that makes a big difference in your answer. Okay. So do be a little careful when you're doing these substitutions here. But this is what we mean by composition. I just need to review this a little bit so that when we get to the functions that are composed together, this won't be something completely new for you. All right, are there questions? This completes the algebra review that I needed to go through before we actually get into the calculus part of the course. Okay? So you should be able to work on that algebra review on Blackboard. I know some of you have already completed it, but you can go ahead and work on that, and it will be due here soon. The actual content of the course, we'll begin that here today, the actual calculus part of the course. And this is chapter 3. The concept that we will look at first is the concept of a limit. And I'm going to try to stay away from the formal definition of limit for just a little while, just to try to get you to understand what a limit really is. And then we'll start talking about mathematically what the definition looks like, and then we'll talk about some shortcuts after a little bit. Let's say, for example, that I give you this function. F of x equals x squared minus 9 over x plus 3. And we probably don't need a calculator for this one, but we might need it for some of the other ones here. Let me go ahead and have you calculate f of 2 for right now. Okay? What would I get if I substituted 2 into this equation for x? Okay, well the numerator is, what, 4 minus 9, so negative 5. The denominator, 2 plus 3, which is 5. So it looks like the value is negative 1. Okay? All right, now, here's where we might need to get out some calculators to help us speed up this process. But I now want to calculate f at 1.99. Okay? So I want to look just a little bit to the left of 2 and see what this value is equal to. Once we get that answer, I want to look just a little bit to the right of x equals 2 and see what happens at 2.01. So if I can get a little bit of help here, what do we get when we plug in 1.99? And then also what do we get when we substitute in 2.01? when you get one of those, please just holler it out. Definitely get a 4.99 in the denominator. I don't know what this numerator will be. Okay, what is the answer? -5.0399. Okay. I'm going to have you double check it again. Make sure there's parentheses around this. Be a little closer to something else here. Negative 1.01. Okay, that's more of what I was hoping it would be. Okay, and what if we substitute in 2.01? What does this? Negative 0.99. Okay. I wanted this first example to work out pretty nicely here, so I picked one where if I just move a little bit to the left of 2, it just moves the answer a little bit, and if I move a little bit to the right of 2, it just moves the answer a little bit the other direction. Okay. Now, the next thing that you can do is you can go ahead and graph this function on your calculator. Okay? And again, use parentheses around both the numerator and denominator. I know what this graph will look like, so I'll just go ahead and sketch it up here on the board. This graph almost looks exactly like a straight line. And in fact, when you graph it on your calculator, it probably will look exactly like a linear function, even though it doesn't appear to be a linear function when we start here. Okay? Here's what we mean when we talk about the concept of a limit. Okay? I'm going to, let's just say that I'm interested in finding out the behavior around the value of 2. So I care about what's happening over here at x equals 2. Okay? We know from what, negative 1. We know from our calculation that this point goes through to negative 1. Okay? What's happening to the left of x equals 2? Okay? Well, we're along this graph, and we just continue to get closer and closer to that particular value of negative 1, don't we? Okay? What's happening on the right side? What if I'm walking along this line? Well, I've got a y value of 5, then 4, then 3, then 2. All the way down, my y value is also getting close to negative 1. This is what we mean when we talk about a limit. Okay, and I'm going to put this up here on the board because this is a common thing. Students make this harder than it needs to be sometimes. A limit is just is basically just a y value that the graph is approaching. And this doesn't seem like too big of a concept at this stage, okay, because we've just done an easy example. I mean, we can see that it looks like the value is getting closer and closer to negative 1. From the right side, it's getting closer and closer to negative 1. And it's exactly negative 1 right at that point. So this doesn't seem like a big discovery that we have made here, okay? But this is the basic concept of a limit. Now, I'm going to change something here, and I'm now going to say, let's look at the limit as f approaches negative 3. Okay? This one will be a little different because what happens if I just try to substitute in negative 3 into this equation? The numerator turns into what? 0, and the denominator turns into what? 0, right? Okay, 9 minus 9, negative 3 plus 3. Everything zeroes out. And so if I try to just actually do the calculation, I end up with 0 divided by 0. And in calculus, this is one of the things we call an indeterminate form. Okay? We can't do 0 divided by 0. Okay? We don't know what that number is. We don't know what that answer is. So what we've got to do is we've got to come up with another way of trying to approximate this value. And the best thing that we can do is use this concept of a limit. Let's see what's happening just a little bit to the left of negative 3, And let's see what's happening just to the right of negative 3. And let's see if they're both coming toward a common value here. Right? So that's the next thing I need you to do. And again, I'm going to ask for your help here. I want to find out what is the value just to the left of negative 3. And then I also want to find out what's the value just to the right of negative 3. So if you could plug in those numbers for me, I'd appreciate it. What are these y values as we look just to the left of negative 3 and just to the right of negative 3? To the left is which one? What's negative 3.01? Okay. And I'll just round it up to negative 3.01. Okay. Let's see, is that, don't know if that's correct. Okay. I think it should be negative 6.01, yeah. Okay, again, maybe just a parenthesis missing there. Okay, you have to be really careful with the parentheses. What about negative 2.99? Negative 5.99. Okay. All right, now, if we wanted to really spend a little more time on this, we could even look a little bit farther to the left. We could look at negative 3.02 and negative 2.98. You know, we can just continue to look at this. But the idea will be is that does it look like both of these values, are we approaching a common y value? Is there some type of a middle ground that it appears we might be getting close to? And the answer is yes. What does it look like we're getting close to? Negative 6. Okay? One side we're a little bit below negative 6, one side we're a little bit above negative 6. But it looks like that if we were to continue this process, it looks like our values are getting closer and closer to a common value of negative 6. And so what we say here, and this is the notation that we will use, okay? We use LIM for limit. In this case, the x value is getting really close to what? The x value is getting close to negative 3. So we say the limit as x approaches negative 3. Let's see if I got a better marker here. Okay. For our function f of x is equal to what? What do we think the value is getting close to as x gets close to negative 3? We think it's getting close to negative 6. And so this is the notation that we use when we talk about limits in calculus. Okay? We list the x value down here, we list the y value over here, and that's why I say that's what a limit really is. It's just what y value is that graph approaching? Well, it looks like it's approaching negative 6 because we're a little bit to the left and then just a little bit to the right. Okay? The big advantage of that, like we said, is that gives us a little bit of an idea of where this graph is at, even though we actually could not make the calculation at negative 3. Okay? So this is a big advantage for us. Truthfully, what this graph looks like, it is a straight line, but over here at negative 3, boy, these markers are all dead here. Okay? At negative 3, there's actually an open hole or an open circle in the graph at that point because we could not substitute in negative 3. Okay? If you remember back to algebra, there were sometimes we had holes in graphs, and this is one of those examples that I chose. But it does make sense because as we get closer to negative 3 from one side and we get closer to negative 3 from the other side, they are both approaching the same number. They're both approaching negative 6. Okay? All right, now, sometimes this is the best that we can do. If we need to approximate a limit, the best we can do is just look at the behavior coming from the left and the behavior coming from the right. Okay? However, there will be other times when there are some tricks that we can use, some algebra tricks, to solve for this without having to do the plugging in and doing the trial and error here. Okay? Whenever you get a case where you've got some type of a 0 over 0 situation, I called it an indeterminate form a little bit ago. 0 over 0, there are lots of algebra tricks that work on 0 over 0 type equations. Okay? And so I want to show you the one that works for this particular example over here. Okay? One of the things that we can try to do in a 0 over 0, if we want to solve this without having to do the trial and error, okay, is we can try to do some factoring on this particular equation and see if anything cancels off. Okay? The numerator is one of these difference of two squares that we talked about last time. What does the numerator factor to? X squared minus 9 can be factored into which two factors? X plus 3, X minus 3. Okay? And this is why I went through difference of two squares the other day, because we will see this quite a bit in the semester here. Okay? And the big advantage of noticing that this factors to X plus 3 and X minus 3 is the fact that this X plus 3 factor is the same in both numerator and denominator. It actually cancels off. So the only piece that is left really is X minus 3, and that's why this graph looks like a linear function, because that's really the only part that's left after we do the cancellation. Okay? Now, if our question said find the limit as x approaches negative 3 for our function f of x, okay, I could not substitute in negative 3 initially because I got 0 divided by 0. But now that I've canceled some stuff off, can I now substitute in negative 3 into what's left? And the answer is yes, and what answer do I get? Negative 6, okay? And that should, that looks good, because this is the exact answer that we came up with when we did this in trial and error mode. Okay? So this is one of the algebra tricks that you can use. If you can ever do some factoring and get some things to cancel off, then you can actually just calculate the limit by plugging in this x value into whatever did not cancel off. And that'll be your answer. Okay? So that's one way to calculate a limit. Now, let's go to another example here. What if we look at this example here? Limit as x goes to 4 of x to the 3 halves minus 8 x plus x to the 1 half plus 6. Minus 6. Okay? So they want us to calculate this particular limit. Right? Again, a limit is just a y value. So it's almost like we've got an equation over here, and we want to know what's happening at x equals 4. Our first step is always just try to plug in x equals 4. Because if we get a numerical answer, then we're finished. We don't have to do anything else. We just calculated the y value. All right, what happens when I substitute in 4, though, this time? Okay, if you plug this in your calculator, 4 to the 3 halves, this will be 8. 8 minus 8 turns into 0. Okay? Denominator. All right, I'll do the more complicated part first. 4 to the 1 half, that's the square root of 4, which is 2. 2 plus another 4 is 6. 6 minus 6, 0. Okay? So I picked another equation that was what we call indeterminate form. We get this 0 over 0 situation. Now, my question is, does anyone know how to factor on this one? There probably is a way, but I don't even know it myself. So this is the reason I brought this problem up. So what if we get to this situation, 0 over 0, and we don't see any factors here? What do we have to fall back on? Well, what did we do here a little bit ago that I just erased? Well, we had to kind of do trial and error. Okay? If we want to find out what the limit of this function is as x gets close to 4, we need to try to evaluate this function at a value just to the left of 4, and we need to try evaluating this function at a value just to the right of 4. Okay? And there's a couple of ways you can do this. If you use your calculators, you can graph this function. Okay, again, making sure that you use parentheses around it. Okay, and you can do a second calculate value and plug in these numbers, or you can use a table feature, or there's many other options. Okay, or you can just actually on your home screen type these in. Okay, anybody got these values? For 3.99 and then for 4.01. Let's see what these values turn out to be. Anybody got them yet? I don't have them down, so I don't know what they are. And I'm not going to get anyone brave enough to volunteer this morning, it doesn't look like. Okay. In general, though, when we type this in, since it is a 0 over 0 situation, okay, we should expect that this number is, if it is some value, and again, I have no idea what these answers are, if it's close to 5, we should expect this number to also be close to 5. Okay, one on each side of the number that we're really looking for. Okay, and whatever that number comes out to be, that's the value that we suspect, or that's the value that we guess for x equals 4. Okay, that's what the limit would equal in this particular case. All right? Okay. So there's that example. There are a section or a group of what they call limit laws or limit rules. They are in your textbook, page 145. Okay. I don't want to go through all of these because it is a lot of theory, but I do want to go through the first couple just as an example here so that you're familiar with them. I'm going to start with number 2 as a possible example. It says the limit as x approaches some number a for f of x plus g of x. Okay? So say we have some type of an equation here, f of x plus g of x. Okay? Maybe it's x squared plus 2 or something. Okay? So we've got this equation, and we want to find the limit as x approaches some number in that particular equation. What this formula says we can do it says that we can split this function apart. We can look at the limit as x goes to a in the first piece, or the first part of the function, the f of x, and then we can do the same thing in the second part. Okay? So we do not have to look at the function as a whole. We can look at the function one piece at a time, find the limit of each one of those individual pieces, and then add them together. And that makes sense. You know, if we're looking at the y value of a function, can't I look at the y value on the first part, the y value on the second part, and then just add them together? And the answer is yes, because that's exactly what happened in the function. Okay? So that's what this is saying. And if you browse through the other examples for rules of limits, they're going to be similar equations to this. The reason I don't spend a lot of time on them, because there's not really any major surprises in here. Okay? Intuition would say that, yeah, this probably works, and that's what happens in all of them, is that there's no big surprises that we would not have expected. Okay? So there's these limit laws that we can use here. Okay? What if we have an example that looks like this? F of x equals 2 divided by x plus 4. Now, just because I think you're probably starting to catch on to what we're going with here, or the direction that we're going here, what's the one interesting x coordinate here that we might be interested in looking at? What value of x is going to create a little bit of a problem here? -4, okay? If I plug in 1, well, there's nothing exciting about that. It's just 2 divided by 5. I've got my answer, okay? If I look at 10, well, again, nothing exciting happens. We just plug in the number, we're finished, okay? But what happens around -4? That's a more interesting question, because when we plug in -4, we get division by 0. And we already know we cannot have division by 0, okay? Now, this one's going to work a little differently than some of the previous examples. Okay? So again, I'll need a little bit of help with calculating on this. Okay? First of all, we know that we cannot just substitute in -4, because we would get 2 divided by 0. Can't do division by 0. So we have to looking at the neighboring points. So what if we actually substitute in a number just a little bit to the left of -4? Okay? All right, and we can probably even do this in our head without the calculator. The numerator just stays at 2. There's no substituting in there. The denominator, what's -3.99 plus 4? Well, that would just be 0.01, wouldn't it? 4 minus 3.99. Okay? 2 divided by 0.01 is equal to what? 200. Sure, so I'm going to go ahead and erase this. And we see that the y value at this point is 200. Okay? Let's look on the other side. Let's look at -4.01 and see what happens. Okay? Again, the numerator is just 2. If I substitute in -4.01, I get -0.01 this time. And so what's 2 divided by -0.01? -200, sure. Okay, so again, I'll erase this and put the simplified value in. Okay, now, what's different about this problem than the previous ones? Well, before, we always had the left side and the right side, they were always approaching at the same number. And in this case, it's a little bit hard to tell what that number might be, because this one's at 200 and this one's at -200. So they're not very close to each other. Okay? So what we can do is let's just continue to look on the left side of this -4. Okay? The graph, I don't know what it looks like, but we got really close. We got to -3.99. What if we go to -3.999? What if we add on another 9 here? Okay? What will that do to my answer? Okay? Well, the numerator is still 2. The denominator this time will be 0.001, just adding an extra decimal point. And so what's 2 divided by 0.001? 2,000. Sure. Okay. And if we continue this process here, what if I get even closer to that value of -4? This one should be what? 20,000, right. Okay, we're just going to continue to add an extra 0 in here. Okay, what is happening to these y values here as I get closer and closer to -4? They continue to get larger, and they will continue to get larger forever. Okay, so what we can say is that as we get really close to -4, these values are going off to infinity. Okay, they just continue to get larger and larger the closer and closer I get to -4. Okay, on the left side over here, what if I get closer and closer to -4 from that direction? Well, this value will turn into -2,000, and then continuing on here, this one's going off towards what? This one's going off toward -infinity, right? Okay. So the behavior on one side is taking us upward to infinity. The behavior on the other side is taking us to -infinity. Okay. So what we would say in this particular problem is that the limit does not exist. If the left side takes you toward one number, the right side takes you to a different number, then we just conclude that the limit does not exist. And this will happen quite a bit. I mean, there'll be a lot of problems where the limit just does not exist. The only time the limit can exist is when both the left and the right side are approaching that same value, okay, which is what some of the earlier examples we saw. Okay. All right, it is time to stop here for today. Have a great weekend, and we'll see you next week.